Good afternoon, everybody. Welcome back. We have a full afternoon still planned for you. So I want to dive in to give enough time to also the other ESA colleagues to present their particular domains. So my name is Angelique van Omberger. I'm a Chief Exploration Scientist, and I will take just very briefly, because our director already talked about it earlier this morning, just to give you a little bit the overall framework for the exploration science, and then I will dive a little bit deeper into the human exploration science activities and to give you some highlights there, and in particular also focus on the outlook. So just to summarize, the Explore 2040 strategy from ESA is focusing in particular on, let's say, three main objectives. It's to have a sustained human presence in low Earth orbit, on the ISS, but of course also beyond. And with human presence, of course, also comes scientific activities and utilization. The second objective is to enable Europeans to explore the moon in the 2030s, and my colleague James will also talk a little bit more about the moon plans that we have. And then we want to eventually prepare taking Europeans to Mars. This is, let's say a little bit more a longer term plan, and Gerard will talk about in particular the robotic precursor activities that we are doing also to prepare for that. Just very briefly, within HRE, within human and robotic exploration, we cover a wide range of platforms and destinations. And of course, within the scientific domain, we target these different platforms in order to prepare eventually for the destinations and for the missions that we have upcoming. I'm not going to go into detail here, but I just want to stress that we have a very diverse portfolio here, in particular also on ground, and that these activities are also critical to de-risk and to prepare as good as possible for eventually these more, let's say, complicated, complex missions that we have upcoming. Then just a few words on the exploration science. So our director already mentioned it this morning, but I think this is a fairly new element for you as a scientific community, because we will now have these two streams of science, which is exploration-focused science and exploration-enabled science. And I just want to spend 1 minute on this, because I do think it's important, because a lot of how we will work with you in the future is going to be built around these two streams. And we're currently working internally to try and really define what do these two things mean and how are we going to implement that. And that is work in progress. And of course, we are happy to keep you also up to date in that. For the exploration-focused science, it's really top-down. It's science that has a high programmatic need and science that needs to be done to meet eventually our exploration objectives. So here ESA will be directing, so to say, the community to help and close those important knowledge gaps. And this can be also very applied, let's say, things. And as mentioned also, there is going to be a very strong link with the technology that we need for the exploration missions. Then when it comes to the second pillar, which is the exploration-enabled science, I think this is the science that most of you have been used to working with ESA on. So this is really the science that is enabled by the exploration that we do and by the platforms we have at our availability. This is coming from the community bottom up and is based on excellence. So it's based on AO-driven processes, announcements of opportunity, where we then select the best science that we then, let's say, implement across our platforms. So this is a little bit the new mindset that we have at ESA. So we will have the two streams. It's not going to be very, I mean, of course, this is a spectrum. It's a lot of activities will fit on both ends of the spectrum. But it is something that we are now working internally together also with our member states to define how can we engage the community best in this way. Then just very briefly want to talk about briefly the thematics, and our director already mentioned it this morning. So for the exploration focused, so I want to say this is specifically for the focused science, we have 4 key thematics. One is local resources, which is really to understand let's say to scout, to understand the abundance, the distribution, but also how can we utilize local resources, for example, on the moon and Mars, to enable our exploration objectives and to enable the human missions in particular. And I know James and Gerard will also talk a little bit more about that. The second element is environments and effects, and I know our director talked about that in particular as well. It's really to understand what are the environments that we're going to send humans to, what are the environments that we're going to explore in, And how will that impact our missions? How will that impact our astronauts, for example, but also the other way around? How will, let's say, us sending missions, for example, to the moon or to Mars, or astronauts there, how will that impact the environments there? And how can we try to make sure to keep them as pristine as possible? So that's also an element, I think, that's very important. And then there is the element of crew health and performance. I think that speaks relatively for itself, is really to understand the physiological adaptations that happen due to a multitude of the space stressors and really the combined effects, but also trying to make sure we have sufficient countermeasures to mitigate them and to keep the level of performance as high as possible. And we will also have a more detailed discussion about that tomorrow. And then the last element is habitation. This is also, of course, strongly driven by technology maturation and what we need to do that. But I think the habitation element is really quite broad in a sense, because it's really everything that allows us to put humans into long-duration spaceflight and to have them live and work in those environments. So it, of course, covers everything related to radiation shielding, but also elements like life support, food production, microbiology. So it's a quite wide range of activities, and here really science and technology need to go hand in hand. So that was it for my general introduction. Now I want to focus a little bit on the human exploration science, and we will have many discussions over the next 2.5 days that focus also on this. So just very briefly, and I know a lot of you in the audience are very much aware of this, but when we look at the human health hazards for, let's say, space exploration, we have 5 big teams. And those of you in the audience that are aware of NASA's Human Research Program, you will see a lot of similarities here with the risk factors. We, of course, have altered gravity. I think that speaks for itself. So it's the combination of microgravity, partial gravity, but also gravitational transitions that is really important for us to understand, especially as we now move towards Artemis and eventually also Mars exploration, because here we really need to understand both at an acute level, but also at a sustained level, how this impacts the human well-being. And I just want to mention that we have several panels on that. You can see them listed here, but of course you've also seen the program, so please keep an eye on those presentations. Then going into space radiation, I think this is one of the biggest showstoppers, and that's also why, and it's a very important topic, that's also why we have a panel later today on it. So really to understand, let's say, the environment, but in particular also trying to mitigate the impact it has on our equipment, but also, of course, on our astronauts. And yeah, we have a few sessions detailing that. Isolation, I think it's something we can all relate to a little bit better after the COVID pandemic. So isolation and confinement, the psychosocial stress of human missions is going to be very important, especially for these long duration, where the distance to Earth is also bigger. And we also have a few dedicated sessions that are going to go into a little bit more detail there. Remoteness, so the distance to Earth, the higher autonomy that crew needs to have, and this of course relates to medical autonomy, but also food production, medical treatment, communication, so those are all important elements. We also have a few sessions on that. And then the last element is the extreme and confined environments that we need to deal with. For example, lunar dust, but also being confined, microbiology of the built habitat and everything related to that. And we also have quite some sessions that will focus in particular there. For the highlights, we've done are ongoing for 2 big bed rest studies. So these are 60-day campaigns. This is quite a very big effort, and we're working with quite a few of you here in the audience to make that work. So we've finalized, or at least the main part of the study is finalized for the BRACE bed rest study. This is a 60-day bed rest study looking at a combination of cycling and artificial gravity as a countermeasure. We've tested 24 subjects over 2 campaigns in the Space Clinic in Toulouse at MEDES. Everything has been going very well. I think some of the MEDES colleagues might have gotten a few extra gray hairs because of running it, but okay, it worked quite well. And of course, we're now doing the follow-up measurements, and we're really looking forward also to see the results. And I'm sure you'll hear about it in some of the sessions tomorrow and on Thursday. In the same frame, this is a little bit of a sister study there. We have BRAVE. This is not looking at cycling, but also at artificial gravity in combination with resistive vibration exercises. So that study is actually ongoing. Campaign 1 is coming to an end now. It will end just before the Christmas break fully. And then we will have a second campaign later next year. This was quite a lot of work. We've been preparing for this for quite a long time, so we're happy that this is finally starting or even completing. And of course, the results from this will also feed into generally our countermeasures and trying to better understand that. And also here we have some sessions related to that. Then I want to briefly talk about another analog that we have, which is dry immersion. We've started, let's say, based on the Russian model that there is. We've now started to implement that also in Europe, and in France in particular there's quite a strong expertise in the model. So we're trying to validate dry immersion as an analog model, and in particular also understand, and I come back to that a bit later, how it compares to the gold standard of bed rest. So we've ran 2 studies, Vivaldi 1 and Vivaldi 2, both with 20 respectively female and male participants. 5-day dry immersion study without any countermeasure. And you can see that the first results have also been published. And I know the, let's say, lead of the dry immersion expert group is also here, Marc-Antoine Cousteau, and he will present a bit of those results also tomorrow. So keep an eye out for that if you have an interest in that. Then some of our ISS experiments have been awarded recently, and I just mentioned a few here that were awarded, let's say, in the last year. The first one is Brain DTI, looking at how the brain adapts to spaceflight, in particular looking at brain structure and function. The team has been awarded with the compelling results in human research from the ISS program, so this is a quite nice award. The PI, Floris Duets, is also here, and he will present a little bit more on the results on day 3. So if you have an interest in that, please check it out. Then we also have Suture in Space, which was also awarded by the ISS program for innovation in human health research. And Monica Monici is also here, and I'm sure she will talk a little bit more. In particular, Suture in Space is looking at wound healing in, let's say, in gravitational environment, let's say microgravity environment, and how mechanical loading or the lack of mechanical loading is impacting the wound healing and the sutures. Then the last one, is Headaches in Space. Also that one got an award for compelling results. And that one was really looking at the frequency of headaches in space, and in particular, how impairing those headaches can also be. The team is not here to my knowledge, but if you have an interest in that, there was a paper recently in Neurology that was published, so please also have a look at that. Then some other highlights. I want to mention that we've started submarine research in collaboration with the Portuguese Navy and the Portuguese Space Agency. So we are looking in particularly at, of course, isolation markers, but also stress markers, because this is a quite stressful environment. But what is very nice is that it's very high fidelity for spaceflight. So by getting some data on these deployments, we hope to be able to expand, let's say, also the knowledge and translate that to exploration missions. And we also have some of the people involved who will maybe mention this or talk about this briefly in one of the sessions later. And then just the last highlight I want to mention is that we recently organized the Space Omics Hackathon. We made use, let's say, of the open science data that's available through the GeneLab, NASA GeneLab portal. And we worked with students and early careers to really try and dive into the data and answer some key questions that we've set up front, in particular in biology. And this was really, it was the first time that we organized it, but it was really a great success and also a great way of showing the importance of open data, and also, of course, in working with, let's say, early careers, younger scientists. So that's something that we definitely want to keep, and we're also looking into whether we can expand that for other topics. Now I want to dive a little bit into the outlook of what is still coming. Just a few things. We currently have an announcement of opportunity open for the Fly feasibility study. I don't know if everybody is aware, but ESA, as part of its project core, selected an astronaut with a disability, John McFall from the UK. We do not yet have a confirmed mission for him. And this is still open for political decision by our member states, but we are really trying to do everything within our, let's say, realm of possibility to make this work. And one thing we want to do with EAO is to, let's say, solicit for science that can target particularly John and in his particular case. So we're looking at really understanding health and safety challenges. When it comes to an astronaut having a prosthetic, we want to look at how we can, let's say, increase inclusivity and diversity in the astronaut corps. Of course, we want to gather also scientific data on this. And then the last thing is, how can we utilize this potential mission, as I mentioned, to be confirmed, to innovate, for example, spacecraft design and operations. Another element I want to mention, and this is something where we are ramping up our efforts, is that we're really looking into tissue chips and organoids, so basically microphysiological models, to try and better understand how space stressors impact humans. And we want to use these models also as a, let's say, parallel to of course, the human research activities that we do. And we currently have set up an expert group together with the community, and we also have an AO open to try and really ramp up these activities, for example, to better understand how space radiation can impact certain tissues. And if you have an interest, we have several people of the team here, including Christiane Ahan, who is leading this, that you can talk to about that. Another outlook is that next year we will run the ESA isolation study at NVIAP in Cologne. It's going to be a 100-day isolation and confinement study. We've recently finalized, let's say, the selection of the experiments, and we will communicate about that very shortly. Here the plan is really to look into the stressors that come, let's say, with the isolation and confinement, but also in a very, let's say, general way. I mean, across the board, we want to really understand also team dynamics, not only at the individual level, but also at the team. And we want to use this also to see how we can maybe test some equipment that we might need for, let's say, higher autonomy missions coming up. We want to see whether we can integrate this also in this mission. One outlook that will start very soon, as I already mentioned, we're trying to validate the dry immersion model and understand how it, let's say, links with bed rest, is that we have a Vivaldi tree study coming up again at MEDES in Toulouse, where we will compare 10 days of bed rest to 10 days of dry immersion, and this is going to be really critical information that can help us to utilize those analogs to the best extent possible, and that we can use it also to validate countermeasures. But of course, they come also with some logistical challenges, so depending on the outcome, we can then tailor, let's say, our studies in validating countermeasures a little bit better. My last slide, I just want to outline that we have now also the approval from our member states to set up an exploration biobank. So the idea is that for all of the studies that we are running, we will collect a set of standard measures related to blood, plasma, we will have urine, maybe hair, saliva, where we will make sure that we can keep some of those samples to make them later available for the community, and that we also keep some samples that we might use or activate later when we have state-of-the-art technologies that can help us to elucidate a little bit better the space stressors at the human level. So that's something that will come out soon, and we look forward also to work with you on that. This was my last slide. I just want to thank the whole team. A lot of the people that you see on the slide are also here. And I kindly hand over to Sébastien. I propose that we go through the presentations and then we do a longer Q&A at the end, and we will also have a coffee break. So I hope that's okay. Thank you.
Thank you, Angelique. So I will continue this presentation, starting just to remember the different platforms we are using. And my presentation will be focusing on the physical sciences, because we talk about the life science, but of course physical sciences is also something that that is really important. Especially most of you are working on, let's say, the project and ISS projects since probably 20 years, and the two aspects of life and physical sciences have been tackled in very important in our program. So maybe I will go to the next one. So physical sciences, at least in ESA, is composed of maybe 6 themes. This is different. It could be different from one agency to another, but usually they are tackling 2 aspects of the phenomena. The fact that you are doing experiments in microgravity, in space usually, and also the other aspect is because you are in space, so the environment, the space environment. So microgravity is really important because you can tackle or understand phenomena that you won't be able to understand in gravity conditions, because you have different density, you have solidification processes, evaporation, change of phase, or multi-phase flow. The 6 themes that we have is usually pretty standard, let's say, in the academic world. So you have the fundamental physics, material science, fluid physics, soft matter or complex fluids, combustion phenomena, and then environment and astrophysics aspect. One of the main aspects, at least working on those projects, is really the collaborative aspect. Currently, we have most of the instruments that are multi-user, multi-platform, and we have something like the statistic is evolving from one year to another, but around 500 scientists. We have 34 countries currently represented, and about 60 industry partners. When I'm talking of industry, it's not the industry who are building the experiment, but the industry that are interested by the research we are doing. Another aspect is that the research that is done is both fundamental and applied. When I'm talking of applied science, is application on Earth and in space, the 2 aspects. And then maybe the other aspect in terms of collaboration, this is not only the collaboration of the science team, so science teams that are just composed of various institutes, but also collaboration between the agencies. Most of the instruments that I will mention just after are very often a collaboration between ESA and other agencies. Of course, European agencies like DLR, CNES, ASI, UK space agencies, and the other partners that we have in Europe, but also NASA, the Russian, and JAXA also are well represented. And we do that also not because only we like collaborate in the international level, it is also because we need that. Most of those experiments are complex and require collaboration to maximize the outcome. I will highlight just the various results we have, and more results will be also highlighted in the different presentations. So the first one is the Parabolic Fly. Parabolic Fly campaign is really useful both for life and physical sciences. Here I wanted to mention that we released recently partial gravity AO that is tackling again both life and physical sciences, but allows also to do research really applied to Moon and Mars conditions. We received a lot of, let's say, proposal for that. The selection process isn't going. In terms of physical sciences, most of those proposals are linked to combustions or multi-phase flow or even granular matter. The other aspect also that our platform that we are using is Sounding Rocket. I wanted to mention that because, as you see on the right-hand pictures, just this morning, Axiom was launched Maser 16 rocket, and on board 3 ESA experiments together with 3 other experiments from DLR. And so all those experiments went back home safely. So they launched the rocket, and then it was bring back to Earth, and then now they are in the lab. For those 3 experiments, 1 was in life science, 2 in physical sciences. And for now, the results look promising. Of course, it needs to be analyzed. The platform that we are using the most, also who are most represented, let's say, in our pool of research project is the International Space Station, of course. And here, what I put is really a snapshot of the different instruments that we are using. And what I think is really interesting is that you have very often very long operation time. Most of those experiments are still running, and they are tackling different aspects. So from material science with EML, Material Science Lab, that is something nearly 15 years of, and still ongoing. We have experiment in heliophysics with solar that is now decommissioned. We had more physical science, let's say fundamental science like PK4, where we have actually some presentation later on this, in this workshop, with a presentation of Michael Pastenik, and soft matter with the soft matter dynamic that is still also running with experiment in various fields, in foam, emulsions, and granular matter. Also an highlight I wanted to mention is that a few weeks ago on Space 631, during a resupply missions, 2 experiments from ESA were sent to the space station in topics that are completely different. So one is what you see on the left-hand side is Euromaterial aging. So this is exposure of material outside of the station. And on the right-hand side, this is a drop coalescence experiment. And what you see on the picture is actually one of those preliminary tests. And so this is just a bubbles, drop with bubbles inside. It makes a nice picture, but this is not what you want when this is performing nominally. There is actually a presentation on day 2 from Michael Boni on exactly this experiment. Also an highlight is for the long-running experiment we have is about EML, the electromagnetic levitator. This summer was organized a 10 years anniversary of this experiment, and we have a number of projects that are represented in the sessions tomorrow, where we have actually a couple of sessions on this experiment. And this is highly also collaborative type of project with representative from Japan, US, and here on the pictures you have people from everywhere, representing also the industry involved in this instrument. Another aspect is a collaborative project that is still running on ISS today, is the soft matter dynamics. So here what you see on the picture is just the ESA astronaut Alexander Guest that is putting the experiment on there. We received recently some also publication that I mentioned here, but I will not go into the detail because we have actually 3 presentations from foam, emulsions, and granular matter experiment with a presentation of Luigi Cristoforini, Anina Salonen, and Matthias Sperl also here. And you have some coarsening videos of foam, but again, you will see more during the presentation of my colleagues. One of the latest highlight I wanted to mention is something that has nothing to do with, let's say, fluid and flow. This is more about atmospheric science, atmospheric physics, and so this is one of the results from the experiment called Axiom, still running and performing very well. And here also we have a presentation by Thorsten Neuber, also tomorrow, after tomorrow, and so I will warmly advise you also to see this presentation because you have a fantastic result. And the good thing also, this is typically also the instrument that goes beyond the original goal. We have a lot of collaboration. Here, this is a paper that is just studying the evolution of the climate for the next 100 years. And that goes beyond, let's say, the line link physics that we were looking for with Axiom. The last highlight I wanted to mention is, of course, the atomic clock that will be launched at the beginning of next year. This is called ASIS, and now we are performing a test and the final test of the instrument before the launch, and now it looks pretty good. The launch is planned on January next year. April next year. And the shipment is planned in January, and so we will have also a presentation on tomorrow on that. And I would like just to thank you for your attention, also my colleagues that are present also today to help out on that. Thanks. And then James Carpenter will continue on the moon activities.
Thank you. Slow. Wait for the slides to come up. Very good. So, good afternoon. So I think the idea of this workshop is to take stock of where we are, what's happened in the programme in the last years, and then to take a look at the future and to give you some idea of what's coming. And so something that's kind of new to our program is the moon. As you saw earlier, exploration of the moon and beyond is something which is coming and growing globally and in ESA. And so what I'd like to give you an idea of today is firstly, a little bit about the moon. My starting assumption is that most of you haven't worked at the moon before, that some of you might have some idea about it, but you may have a limited understanding of the moon and what it offers to us. So I'd like to give you some idea initially of what the moon's about, what science and research at the moon is going to be about, and then to give you a snapshot of where we are today in terms of our science program at the moon, and then give you a glimpse of what's to come. And if you have questions on that, we can explore that a little bit more at the end. So if you go to the next slide, please. The first thing I would like you to understand is that we have not explored the moon. We have been to the moon, but we have not explored it yet. So we have a few missions that have gone to a few locations. You can see some of them here. These have been mostly US missions from the 1970s. The Chinese have been there recently. But we've explored a really tiny part of an area which has the size of Africa, which is extremely diverse, and which we really have only glimpsed just a snapshot of. One of the things we have learned following recent remote sensing instruments from the last few years is that the places that we have been on the lunar surface, the places we've taken samples from, brought them back to Earth, the samples that have told us really that become the cornerstone of our understanding of planetary formation and evolution, come from places on the moon which are unrepresentative of the moon as a whole. So if there's one thing we've learned from recent years, is that to understand the moon and what it can tell us about the whole of the history of the solar system, we have to go back there and go to places we haven't been before. And I think what we're seeing globally with activities around the world is that everybody's going back, and that we're going to see really an explosion, a renaissance, and a huge growth in lunar exploration in the years to come, which is going to bring enormous opportunities for science. So if you go to the next slide. So we have not explored the moon, but we will. And so you already saw this morning from Daniel Neuschwander some indication of the kind of things that we're going to be doing within ESA, the way we're going to contribute, and the way some of our ambitions exist to grow our program and to provide, to uplift science, create new opportunities for research. And what you see in here is a visualization of the Argonaut lander deploying science activities, deploying payloads to the surface of the moon, collecting samples, supporting crew activities that we look to be actively involved with in the years to come through our partnerships with international partners. And so when we're all there, what is the science that we're going to be doing? Well, if you go to the next slide, you'll see that the first thing is that the moon is an archive. In the next slide, I think, great, is an archive of the whole of solar system history. So the moon has geologically not changed very much in a long time, so it preserves some of the fundamental principles of how planetary forms and evolve. Is also something that has sat there and recorded events throughout the whole of solar system history. So early bombardment of the inner solar system, things that affected all of the inner solar system, including the early Earth, are preserved on the lunar surface in a way that they're not anywhere else. The history of our own star, the history of interstellar matter falling into the solar system, all of these things are preserved on the moon and are waiting for us to find them, to retrieve them, to investigate them in situ, and to bring them back. And actually, the moon is the only place in the solar system where we can go to do this work, particularly exploring the early epochs of the Earth's history too. In the next slide. The moon is also a platform where we can perform fundamental research. So it's a partial G environment, which provides us a unique access. It's also somewhere where there's physics and astrophysics, astronomy that we can't do anywhere else. So what you see here is just an artist's visualization of what the cosmic radio sky might look like at long wavelengths from the lunar far side. So this is just one example, but the lunar far side is the only place in the solar system where you can't see Earth in radio. So it's a radio quiet place. It's somewhere you can go to observe potentially the cosmic dawn, long wavelength radio from the cosmic dawn, the era at the beginning of the universe when the earliest cosmic structures are being formed. My personal conviction is that sometime around 2040, we're going to see the beginning of a far-side lunar observatory, somewhere where it'd be a big science project to observe these things for the very first time. We see activity growing around the world towards this as one of many sort of big science objectives that the moon and access to the moon can enable. And so the sorts of things we need to think about are how we're going to prepare ourselves to be participants in these big global fundamental science, fundamental physics projects that are going to come in the decades to come. Next slide, please. The Moon also has an extremely complex and dynamic environment. So it sits exposed to galactic cosmic rays. It also is exposed to solar energetic protons and the solar wind. These interact with the surface. They create a very dynamic, very complex environment combining plasma, charging, dust, the formation and the mobility of water and other volatiles around the lunar surface. This is an environment that is very fragile. The total mass of the lunar exosphere, its tenuous atmosphere, is about the same as the exhaust plume from a single landing. And so one of the things we've understood is that if you want to understand this environment as an example of well-preserved surface-bound exosphere, something which is analogous to any airless body in the solar system, but which is accessible to us, the only time in human history we'll get to do that is now. And if you want to understand our impacts on that environment and how it's changing, then we have to start that work now. It's also important for us to understand this environment because we're going to have to live there and work there. And it's going to affect the way we build our systems, the way we explore, the kind of technology we deploy and how we use them. And so, as you heard earlier on, understanding this environment, understanding its impacts on our activities, and understanding the impact of our activities on that environment is an important priority for the future of our program. Next slide, please. The Moon also has resources. And as you heard earlier on, these resources are things that are going to be enabling for the long-term exploration plans. It's something, learning how to work with and to use resources that we find locally is something that we're going to have to learn to do if you want to explore further into the solar system. The Moon is the place we're going to learn to do that. Now, we also find that there are lots of opportunities that may have sort of future implications for terrestrial applications. And internationally, we see that understanding the potential utility of lunar resources, where they are, how much there is, what it would take to use them to allow decisions to be made about their future utilization, but also to inform sort of big international conversation that's happening about how we regulate our activities, how we control, what is the legal environment surrounding how we access and use these resources, has to be based on a knowledge base that we haven't got yet. And so an important activity in the coming years will be to establish the knowledge base upon which we build all our future decisions about using the resources of the Moon and later on in the solar system. So the Moon can be a source of water ice, it can be a source of hydrogen and oxygen as propellant, it can be a source of minerals, of metals, of other materials. And so we need to understand these things and where they might be and how we might use them. Next slide, please. And so all of our lunar activities today, up until today when we talked about Explore 2040, for us we would date back beyond, but I think the starting point for us today was 2019 and the publication of two important documents for us, which were the ESA Strategy for Science at the Moon and the ESA Strategy for Space Resources. And some people in this room were involved in generating those documents, and thank you very much, and they have been the thing we've built off to get to where we are today. Noting that at that time, we didn't have any ESA lunar missions specifically, and we really tried to work out how do we build on what we have available today with the pieces that we have available in Europe today to do something which is achievable but ambitious and really sets a strong position for the future. And so in the next slides, I'm going to give you an overview of what we have achieved, where we are today, and then just to finish with where I think we're going to go next. Next slide, please. So here are a list, and this is quite small, but hopefully you can see these slides later on and you can examine them in a bit more detail. But here are the ESA payloads for lunar science and technology that we have either built and flown or that are ready to fly today on future missions. So on the top left of the slide, you'll see the Peregrine Ion Trap Mass Spectrometer. This was a mass spectrometer, a spin-out from Prospect that you heard about earlier, and I'll talk about in a minute. This was intended to look at the lunar exosphere and the impact of a lander on the way that a lander would affect that lunar exosphere. That was on the first ever commercial lunar mission from the US, involved in the US CLPS program, Commercial Lunar Payload Services program from Astrobotic. It didn't make it to the Moon, but we were able to test the instrument, and actually the instrument worked perfectly. It was as a demonstration of the instrumentation. It was a success, and the team did extremely well to do that. So that didn't make it to the Moon, but it did set the tone for the future. On the right-hand side of this image, and you heard about this already, we had the negative ions at the lunar surface instrument, which is built by the Swedish Institute of Space Physics for us. That flew on the Chinese Chang'e 6 mission, which was really just the most extraordinary mission. It was really quite an experience to be able to be involved in that. But that instrument made the first discovery of negative ions as a part of the lunar, an important part of the lunar environment. And that operated earlier this year. On the bottom left, we have a lunar laser retroreflector called Moonlight, not to be confused with Moonlight, the communication service, but Moonlight, a laser retroreflector which you laser from Earth to get precise ranging. So this will fly in October of next year, again as a partnership with NASA on a commercial lunar lander to be taken by Intuitive Machines. It will allow precise laser ranging to a place called Reiner Gamma. It will combine with the existing laser retroreflectors which were deployed by Apollo. This particular reflector is much higher performing than those that are on Apollo, has a higher optical performance, allowing us to both do the geophysical measurements that those enable, but also will allow us to test some properties of general relativity, and so allows of both fundamental physics and geosciences. And this will become part of, I think, a growing array of ranging stations on the moon, and is also a capability that will become a part of the ArgoNet payload, which is a communications and navigation system associated with Moonlight that will be on the first Argonaut mission. And at the bottom of the screen, you see LandCam X, which is a precision landing camera technology demonstrator, again flying with a commercial lunar mission in about 12 months' time. Next slide, please. We also have a number of developments. On the far left is Prospect. You heard about that earlier. This is an extraordinary machine. Was originally developed for the part of the Russian cooperation on Luna 27. It's now, since that cooperation was ended, it's been moved on to a commercial lunar mission, which will be delivered by Astrobotic. It's a partnership with the United States, with NASA. This will drill to a meter beneath the surface in the lunar polar regions, extract samples, keeping them cryogenically cold, transfer them into a lab where they'll be sealed, imaged, heated. The volatile gases will be removed. They'll be processed and analyzed in a very comprehensive way for both chemical and isotopic properties. And then we also have the ability to perform some in situ resource utilization chemical experiments to demonstrate the extraction of oxygen from minerals, an extremely powerful machine. Spinning out from that, we had the EMS on the Peregrine ion trap mass spectrometer I mentioned earlier. It's also the basis for the exosphere mass spectrometer on the bottom right here, which is an instrument that's going to go on the Japanese LUPEX polar rover mission, planned for 2027, I think. We also have a wideband technology demonstrator looking at surface-to-surface communications, which is again going with a commercial lunar lander delivered by iSpace. And above that, we have a permittivity sensor. Again, it's a sensor spun out from the Prospect payload development, which is going to be a partnership with the United Arab Emirates on their Rashid 3 rover. Again, it's a way of measuring water ice composition beneath the surface. So that's what we've managed to do on the lunar surface, working in partnership with both commercial actors and international partners. So if you go to the next slide, you move up into orbit. You heard earlier about the Gateway. So the Gateway is this human-tended station that's in lunar orbit. ESA are providing the habitats, providing the refueling capability, providing the windows, and the communications capability, providing the service module for Orion. We're also providing the 2 of the first payloads that are going to be launched with the first elements of Gateway. We have ESA, which is the European Radiation Sensor Array, which goes outside, and IDA, the Internal Dosimetry Array. This will provide a really comprehensive characterization and measurements of the radiation environment, both outside and inside Gateway. That's a really important preparation for future exploration. It also provides a baseline for any other radiation science you might want to do on Gateway, and we're preparing things for the future. Moving on then to the next slide, we're looking at human research that can be done on Gateway 2. Yesterday, so it's a little bit late, but yesterday was the closing date for a request for ideas for human health research that can be performed on Gateway. We're looking forward to analyzing the results of that RFI, which is performed in collaboration with our international partners, to work out what research we might be able to do on Gateway and how you might be able to use that effectively as a platform to prepare for the future. So moving on then down to into the future, that's what we've been able to establish based on the work that came before. With Explore 2040, we're really starting a new era. I think you heard from Daniel this morning an extremely ambitious vision for where we would like to go, a realistic take on where we are today, but demonstrating the ambition to expand and grow our program and grow our role in exploration. So for us, in terms of we think of science at the moon, we're going to be looking at local resources and understanding those better and how we might use them. We want to understand the lunar environment and its effects, both on systems, on technologies, and on biology. We want to understand crew health and performance in that environment and how we can optimize that. We want to look at habitation, but also look at enabled science and how we can use the capabilities we have at the moon, how we can build all these things we're putting together to really be an enabler for some world-class science that cannot be achieved anywhere else, as we look into fundamental physics, biology, and gaze back into the origins of the cosmos. So that, I hope, gives you some perspective for the future, and I hope that when we come back here in a couple of years' time for the next meeting, there'll be a lot of lunar people in this room as well, and we can talk about some of the successes of recent years and give you a really clear vision and outlook on what to expect in the future program. Thank you very much. And with that, I'll hand over to Gerhard, who's going to give you the lowdown on Mars.
Thank you, James. Good afternoon. Like James, I assume that most of you have no dealings with Mars, and so I will give you a little introduction. I will not talk much about the mission that generated this picture, Mars Express. It's an ESA mission. It's managed by the Director of Science. I will focus on the Exploration Directorate missions. But this is a beautiful project that's running for quite some time now. It's still generating great science. I will do it myself. Couple of snapshots about Mars as a planet. I want to go back to the presentation that James just made about the moon. The moon is very important for us because it stabilizes our rotation axis. Mars has moons, very, very small captured asteroids that cannot really affect the stability of the rotational axis. That's why it's tilting from time to time and really plays havoc with the climate. Luckily, we have the moon. The size and the distance from our planet, that is right for us. So Mars has some interesting challenges in terms of climate modifications over time. Mars is a big planet, but it's much smaller than Earth. Just to put it in context here that I mentioned, it's about half the size diameter. But the surface area of Mars is as large as the land area on Earth. So there's a lot to explore, and it's very diverse. Also, the geography that you see on Mars is pretty impressive. See, here is just the comparison with the highest mountain we have on Earth. On Mars, you have the highest volcano in the solar system, many times higher than Mount Everest. Also, in terms of the valley formation or valleys, you have here the Grand Canyon compared to the Valles Marineris. So the geography you have on Mars is substantial, and with that goes also diversity. One term you will hear from time to time when you're in a room with a Mars geek is the term SOL. It's a Mars day. It's a little bit longer than an Earth day, not much, but that's what we call SOL. So when you hear things about rover operation, things like that, how many sols is something on the surface, how many sol does it take to drill down, that's what it means. It's a little bit more than a Mars day. Mars is further away from the sun than we are. I have to update this graph. I don't like the average distance because the orbit of Mars is very elliptical. So average distance really doesn't tell much. But in general, it's much further away than we are, and a very elliptical orbit, which means the seasons are also very different in length. And in total, it takes about 2 Earth years to complete 1 Mars year, just to put it in the context. One very visible feature on Mars, already visible from telescopes here on Earth, is the global dichotomy. You have on the one part of Mars, which is very, at least looks from a telescope, very boring, and what we call the lowlands. And the other part is very, it looks interesting because there are lots of craters. It's a highland. It's a very old terrain on Mars. We cannot land there because it's too old, but it covers more or less half the planet. It's not accessible to us today with our landing system. That's the oldest part. I will come back to the global dichotomy a little bit later. But this is just a snapshot about the planet Mars. Not going to the missions to the Mars Express, I will start with TGO, Trace Gas Orbiter, our workhorse around Mars, generating more than half the data return from all the surface assets inside Curiosity, Perseverance. More than half, sometimes between 60 and 70%, comes back through our orbiter, through the Trace Gas Orbiter. So it's a really essential communication asset providing relay data for the surface assets that are there. On top of being a workhorse for the data relay, it's a workhorse for science. It generates great science. I cannot go into all the details, but I'll just use one example here, the methane story. It's an interesting one because methane can be generated two ways. On Earth, a lot of methane, most of the methane is generated by biology. So it could be also a biomarker. But of course, you can also generate methane abiotically. And we don't know what is the situation on Mars. We just know their data from the surface, from the Curiosity mission, the NASA Curiosity mission, that is measuring methane over several years at different amounts, which was interesting when we got the data originally. Didn't understand why it's fluctuating that way it is actually. Now the other problem is that we have today is the Trace Gas Orbiter, much higher sensitivity in measuring methane, measures the methane from orbit. And the problem is it does not measure the methane. So even at the same time as Curiosity measures methane on the surface, we don't see it from orbit. Both data sets are robust. They are real data. It's not fake data. I think the majority of the community is convinced of that. We just don't understand the dynamics of methane there until recently. A discovery of the Trace Gas Orbiter mission was hydrogen chloride in the atmosphere, first time. A few years ago, it was published by our Russian colleagues on the science team. And recently, some more work into the dynamic of hydrogen chloride and what it does to the other constituents of the atmosphere. And one result of these studies, which has been published already, is it has an impact on the lifetime of methane in the atmosphere. Now, that could explain the difference of the data that we see from the ground and from orbit. So this methane story is a developing story for decades already. It was the first time that methane was measured on Mars. We are now closer to understanding why we see a certain profile of methane on the surface changing with seasons, and that plays an important role in there, and why we don't see it from orbit. So that's just one thing where it is a thing that we want to understand about the planet Mars, and we focused very much on this one thing, on the methane, and the discovery of another constituent in the atmosphere might give us actually the answer to understand the dynamics. So this is the Trace Gas Orbiter. That's an asset in Mars orbit right now. The next step, following also what our director explained to us in the morning, is to go to the surface. And for that, I show you a short video, I think, if it works. October 2028 opens the launch window for the Rosalind Franklin rover. And you have heard already in the morning, we had to switch the partnership because of the Russian invasion of Ukraine. It was already scheduled for launch a number of years ago. So the science team is ready, but we had to change the partnership. We had to develop new systems, including the EDL system. We didn't have to change anything really on the rover. And the science team, 500 plus, is ready to go to Mars. In the end, it will be better mission because we have more time to prepare. a simulation going on this week. I think it's also risk reduction that we have a new partnership. One of the features that is very important and I want to mention here is this. Out of the 500 people, we have divided the science up in different groups. One group worked on a geological map of the landing site. And some people that see the video that you've just seen before, they always ask, why do you see so much water at the end? Where do you find the water on Mars? Well, that's one reason why this landing site was picked. I mentioned at the beginning of my presentation the dichotomy and the lowlands in the north. There's one hypothesis is there was a global ocean, not a global ocean, an ocean on the northern part. And that's one reason why we picked this place, is to see the residues of this ocean. It's very similar to what Perseverance is doing in Jezero Crater. From orbit, we have seen indications, morphological but also chemical indication that water was present there, long-standing water. But it's an indication from orbit. On the surface, Perseverance measured it. Now we know we had water there, long-standing, at least 3 episodes. Here we're very similar. We have indications from orbit, and with ExoMars we want to find out the truth. So this is a geological map that will help us with the strategic and tactical planning. One of the strategic planning exercises going on right now. The team of about 80 people did a great job there, putting together data from different missions, NASA missions, ESA missions, putting also data together from different instruments to react quicker once the rover is on the surface and you move from the strategic to the tactical operation. They have put together a simulation tool, so it's not only a map that you can put on your desk or on the wall. There's actually a simulation tool that you can use, integrating all the different data inputs from the different mission and instruments. Like I mentioned before, you can zoom in, zoom out, and play. You can play around doing the simulation exercise, but this tool will be used for the tactical operation once the rover is on the surface. One thing that I also want to mention, because you've heard it in the morning from our director, you heard it also just before me from James, drilling on the moon. We also have the drill here on Mars going down 2 meters. So this will provide actually the samples that we then can analyze in the laboratory on the rover. That's the first time we'll actually drill in the subsurface of another planet. It's uncharted territory. On top of bringing up samples, we also have an instrument on the drill stem. And what is very important, a ground-penetrating radar at the back of the rover to make an informed decision where to drill and where not to drill. So this is the next step. The rover is currently undergoing some refurbishment, or some of the instruments, because we use the time to make it better. But essentially, we are ready to go from the rover side and from the payload side. And the instrument team and the science team is really eager to finally get to Mars. So that's the second step, from orbit to the surface. And the third step, I'll show you now another video. The next step is bringing Mars to Earth. The first element of the next step is already on Mars. I mentioned it before. It's the Perseverance rover collecting samples as we speak. And these samples will then be transferred to another spacecraft that will need to be launched to Mars. Then the samples will be transferred. Up to 30 sample tubes can be transferred. And to just put it in context, we are not talking about 400 kilograms like Apollo samples. We are talking here about 400 grams material. Well selected, 400 grams. Then we have to launch this whole thing, and this will be the first launch from another planet. The atmosphere makes a difference. It's not like the moon. Like you've heard in the morning, then you have a small, not that size, bigger than that. With the 30 low mass orbit, 300 each kilometer. And then another spacecraft, the Earth Return Orbiter, will have to spot it from a distance of several thousand kilometers and catch it. And this spacecraft is big. It's bigger than all spacecrafts together that are around Mars today. Then the thing has to bring it back to Earth and release it for a landing currently planned at the Utah Testing Training Range. And like our director said in the morning, the architecture is currently under discussion. So NASA is reviewing at the moment a number of industry proposals, but there are some essential elements here that won't change. One is Perseverance is on Mars in collecting samples. The other is ERO is very well in the advanced implementation phase, so we're sticking to our commitment. It's the immediate step to bring this, to land actually another spacecraft on Mars and transfer the sample from Perseverance to ERO that is currently under re-architecture. So that's the family portrait of what's on Perseverance right now. We have the three interesting looking gold shining things, which are reference tubes to measure witness tubes. So when we bring back the sample, we see something weird, we can go back to the witness tubes and see it's maybe terrestrial contamination. The first sample tube that looks very shiny, actually it's the second one on the top row from the left. It's an atmospheric sample. Was not supposed to be an atmospheric sample, but it was a rock acquisition that didn't work well. But now we call it the atmospheric sample. And the rest are essentially sedimentary igneous rocks. Two of them are regolith and dust samples. The regolith and dust samples are very important to feed forward human exploration. This, you can see it maybe just from the pictures. We also have a lot of in situ data from Perseverance. These samples are very, very tricky. That we know already. They're very heterogeneous. And they really require the capabilities of terrestrial laboratories in terms of preparing the samples and analyzing the samples and going back once you have the first data sets. Very difficult to interpret. The science team, Perseverance science team, for some of them, the early samples, they discussed for half a year if this sample is now igneous or sedimentary. So it's really difficult to interpret the sample. Mars is not Earth. At the time when Perseverance were starting to pick up the first samples and we saw some of the challenges from the physical properties, but also the chemistry we can see, we realized we need to beef up a little bit our activities in terms of what do we do once the samples are back? How do we actually extract the samples from the sample tubes? Sample tubes are well designed to house the sample, to seal the sample, and keep them nice and pristine. They're not well designed to open it easily. So there are a number of steps that we're currently undertaking to figure out how we can open the sample tubes without compromising the science we want to do with the samples. How we do the preliminary characterization of the individual samples so that we make informed decisions about the scientific investigation we can do with the various samples and so forth. In order to do that properly, we need analogs. Like I said before, Earth or Mars is not Earth. So you don't find a place on Earth that is the perfect analog for Mars. And that's why we've chartered a team within the Mars Sample Return Science team to work on analog, to work on where to find the perfect analog for certain properties of the samples that we need for certain technical developments. And we have done now a number of field trips, and I just show you one example here. The idea was always to correlate the samples you have on the rover and the properties what you want to see with to do certain developments, and then find the right place on Earth to get some analogs. And there are 2 examples, went to Scotland, went to Oregon, and more or less get back half a ton of material from the different sites. Now we have covered 5 sites. Next year we go most likely to 2 more sites. And this will be then used for the different developments. Now, that's the fun part, to go out in the field to collect rocks. But you know, this is not the end of the story, of course. You need to categorize it. You put it in a catalog, and then you make it available, not only for the program and the project, but also for the science community. And that's what we are doing at the moment, actually. We have established an MSR analog sample library that collects all the rocks. We have about 1.5 tons now over there. This will be characterized by a company, and then we'll make it available. The data will be available through the Planetary Science Archive of ESA, and we make then the samples available. They're already available to the science community, and not only to the program and project. So we are open for business. We opened last week, and you can actually already request samples from this analog sample library. So that's one thing that we have done. This will be used probably for the next decade or longer in parallel to the mass sample return activities. The next milestone that we achieved is planning the science utilization phase. It's another achievement. We have established the measurement definition team. It's a science definition team to see what can we do with the samples that we get back. The big advantage of this mass sample return campaign is, unlike an in situ mission, you know, when you define the in situ mission that goes to Mars, you define a payload. You have some orbital reconnaissance, but you really don't know what samples you will actually get at the end when you're there. We know exactly which samples we get back, so we can really tailor the utilization phase much better. So this team is finished now. They're writing up their report. What has been identified are about 88 investigations that will cover the primary science objectives of mass sample return. There will not be all the investigations that you can do on the sample, but the 88 should match actually the major science objective of MSR, and there will be many more following up on that. But these will now be used as a baseline to define the planning for the science utilization, the instrument procurement, and the sample receiving facility design. So the performance and capabilities of the sample receiving facility will have to match the investigation you need to do to meet the science objectives. So another achievement in a way of getting samples back and maximizing the science utilization. So enough about mass sample return. You've seen we're doing something from orbit today, generating a lot of science data. We're preparing the next step, landing on Mars with a very, very complex payload and the first time drilling in another planet. And then we're engaging right now in another enterprise, the most complex robotic exploration enterprise in the solar system of NASA and ESA. Last but not least, Happy New Year. It's Happy New Mars Year. I don't want to forget that. It's just started. Mars Year 38. So if you have a New Year's resolution for Mars, I mean, it's still not too late, I guess. Mine is to have another Mars science conference, Mars Sample Return Science Conference. We had the last one in Berlin a while ago. It's time for another one. So in this Mars Year 38, I want to have another one. And with that, I'd like to thank you for your attention. And I think I hand over now to Angelique.
I will not take too much of your time, but just on behalf of the team, I want to take a few minutes just to give a little bit of an outlook of upcoming opportunities we have in the near future, because of course we don't get a chance very often to have the community in one place, so we just want to make sure that you're aware of what's going to come up in the future, and then we can open up the floor for questions later. So this is more for students, but I know there's also some students here, or if you have students in your lab. We currently have a few open internships for exploration science. You can see the full list here, so it's mostly in life and physical sciences. I do unfortunately need to say that the deadline is coming quite quickly. So the deadline is the 30th of November. But please, if you have students in any of these areas mentioned here, so we have food production, radiation microbiology, life sciences, space omics, quantum biology, quantum sensing, metallic alloys and using X-ray, and then also water extraction on the moon. Please feel free to put them in touch with one of the ESA colleagues or to have a look on the ESA Jobs website. If you navigate to the ESA website, you can easily find all the descriptions there. And by the way, there's many other internships at the whole directorate and also at ESA level, so there might also be other activities there that might be interesting. Another thing I want to mention is that we currently have an open call. We're soliciting for a new research MD for our Concordia activities. So Concordia is a research station at the Antarctic continent that is run by IPEF and PNRA, respectively the French and Italian polar organizations. And we have a strong collaboration with them to every year run a biomedical complement of research, in particularly focusing, of course, on human exploration elements. So every year we select, jointly with our partners at IPEF and PNRA, a doctor who goes on site and who basically implements the whole program on behalf of ESA. So we're now soliciting for the new call, so for the upcoming winter over 2026 season. And the deadline is at the end of January. So also here, if you yourself or you might know colleagues that are interested, please feel free to make them aware of the opportunity. Another thing I just want to mention, and this is mostly for the life sciences community, is we have CUBIC, which is an incubator that we have on the space station, which has served quite well our biology research. We have a 20-year event next year, 16th and 17th of April at ESTEC, where we will cover some of the main science results, lessons learned, but also perspectives for the future. So if you have an interest, please mark the dates in your calendar, and we'd gladly welcome you at ESTEC then. This is then moving to the moon. Just want to give you an outlook that we, and this is a first one, but we are buying commercial data from Puli Space. They have an upcoming instrument which is called Puli Lunar Water Snooper, and I have to say this is probably my favorite name of a science activity that I've heard so far. But we are basically buying data from them, and Puli will look at water at the lunar surface. They will detect neutrons, and by that they can infer. And what's interesting is that part of the instrument will also be placed on a hopper, so the hopper will go to different locations and will take samples there. If everything goes well, this data will be made available to ESA, to us, because we've bought the data. But of course, we want to work with the scientific community to help us to analyze that data and to exploit that data. So we will release a call, or actually an invitation to tender early next year. The mission will take place end of February, March, right now? Yeah, end of February, on the Intuitive Machines Mission 2. So if you have an interest in this topic, please keep an eye out or get in touch with James so that you can be made aware when this comes out. And then we have a whole bunch of announcements of opportunities that are either open or will open imminently, and I just briefly want to talk through them. So we have Parabolic Flight. This is a continuously open research announcement, and I think some of you are very familiar with that. We have Drop Tower, but also ground-based facilities, including radiation accelerator facilities. Those are continuously open. We will have a new call for EBER, so investigations into biological and physical effects of radiation, together with the colleagues from GSI in Darmstadt. That will open early next year. This is usually let's say, 2-year cycle. So every 2 years we open up the AO, so we have a new one coming up. I already mentioned we have an open call for the tissue chip and organoid research on ground, so for making use of those models to try and get a better understanding of how space stressors impact human tissue. That's currently open and will close end of January. We will have a new sounding rocket AO coming up. So Sebastien mentioned the launch that we had this morning. We will open up the AO early 2025. And this allows for, let's say, mostly physical sciences, but also biology research, and gives up to 6 minutes, 7 minutes of microgravity. For Concordia, I briefly talked about it earlier. We have an AO coming up early next year, together with EPEV and PNRA, where we will select a new batch of experiments to be implemented on the station. And we will also have an AO for the Tempus EML as a preparation on parabolic flight as a preparation for ISS, which will also open early next year. Then for ISS and LEO, we mentioned the Fly Feasibility AO, so looking into John McFall as an astronaut with a disability and to cover some scientific topics there. That's currently open. Deadline is mid-January. And we will also have an announcement of opportunity for transparent alloys on the ISS, which is planned to open actually still this year, so in the next few days or weeks. Then for Moon and Cislunar, we have an upcoming, but this is planned. We cannot yet give you a date, but please keep an eye out. We will have let's say, science team or definition team for a scouting rover on the Moon. And we also plan to set up a team to advise and, let's say, recommend on cislunar radiation activities. We've mentioned ESA-HRE, but of course we want to keep a strong leadership there also in Europe. And then for Mars, the director this morning talked about upcoming missions. So we would have Lightship, which is the EP tug, but also Medal, which is the, let's say, the lander, the heavy lander that will come up. So here we will also ask the community for, we will have an AO for payloads of opportunity for Lightship, and we will have a science definition call for Medal, and those are planned to be opened early 2025. Just to mention, all the opportunities are on our website, scispace.esa.int. We might change the name at some point, but for now it's still there. And we also advertise all of our AOs on the OSIP platform of ESA, so you can find all the info there. And then just one last thing I want to mention is we have an HRE data archive. You can see the list, the link listed there, where basically we try to collect all the information of the investigations we run across the portfolio of our platforms and destinations. And for non-human data, most of the data can also be found there. This is something that we're doing retrospectively, but of course prospectively we also want to make sure that any data that we collect on our platforms is being retained there and is made available for the community. And with that, I think we can close our presentations. Thank you very much for your attention. I know this was a long session, but I hope you got a good overview and glimpse of the, let's say, the breadth of our portfolio. And of course, we're happy to take any questions. We have a little bit of time before we go to the next presentation. So please, if you have any questions for me or for the other colleagues, now is the time. Thank you. Any questions? One question.
Hi, thanks for the presentations. I'm Rodrigo from Karolinska Institute in Sweden. My question goes to you, Angelique, and the exploration science focused. How this top-down approach will be implemented by ESA to secure that mostly all the countries that belong to ESA has the same opportunity to access this top-down approach to that science?
I think it's a very valid question. I'm not sure I can answer it today because we are currently working internally with the team, but of course also with our member states to come to an approach that works. What is clear is that we will need to follow a different way of implementing this exploration-focused science. For the enabled science, we are used to working through AOs, through a selection, and then of course scientists, I mean ESA funds, let's say, the opportunity or the access to the platform, and then scientists get either national funding through their agency or through any other ways to do the science. For exploration-focused science, that most likely won't work. We won't be able to tell exactly what we want scientists to do and then say, now we're not going to fund you to do it. So we need to find a different model of doing that type of science. Rodrigo, I know you have a life sciences background, so you might be familiar also with NASA's HRP and how they do calls. So they can sometimes be very directed calls. And then, of course, when you get selected, you also get a grant with that. So that's an ongoing discussion that we have. We know this is very important science that we need to do, so we also need to make sure that we're properly resourced to support the community to help us. We do not have the internal resources to do all of those scientific activities on the ESA side, so we really need to rely strongly on the community there. But of course, we then also need to come with incentives for the community. With regards to the second part of your question on how do we make sure that, let's say, communities from the different ESA member states get equal opportunities, I actually think for this exploration-focused science, we might even have more opportunities to engage across, let's say, the participating states. And that is something that we always have to keep in mind when we do any type of activity on the ESA side. This is, of course, something that's very important for us, but also for our member states. I hope that answered the question. And of course, this is to be continued. We are now in a critical phase in the preparation for the upcoming ministerial, but this element of exploration-focused science has already been accepted by our member states. Now, of course, it's up to us to come with a proposal for the concrete implementation. And as soon as we have more clarity on that, we will also take the opportunity to share that with the community whenever we can.
Thank you.
Any other questions? I think we need to fill the time because I haven't seen Sławoj back from his meeting and he's supposed to give the next presentation.
I'll take a question to fill in the time then. But seriously, first of all, I'm Adrianos. I'm a medical doctor. I work as a flight surgeon in the European Astronaut Center. We may already have this, but I'm not aware of it. So my question is, do we, as Europe or ESA, have published the priorities in research in its category for exploration? So for example, do we have a priority as in, I don't know, in the neurocognitive sector, we should look in this and this and this? Or in the material sciences, you know, the priorities are this and this and this. Thanks.
Yes, thank you, Adrianus. That's a very good question. So I know there's many people from the community here who were involved in, let's say, prioritization activities in the past and strategy in the past at ESA. So we have a lot of white papers coming from the community bottom up as to what, according to the community, are, let's say, key priorities or key focus areas. And actually, we haven't mentioned it. We should have mentioned it. But we have now also a collection at Nature NPJ Microgravity, where we have a large collection of more than 40 papers outlining in the different domains what are the key criticalities. I think what has been missing in the past, and that's where we come to the exploration focused, is that we try to merge it with the exploration objectives that we have as Europe, as an agency, together with the member states, and that we try to merge it. And I gave one concrete example where I think we are really starting to do that now, and you can see that by the presence of yourself and May-Britt and John and Anna, is that we are really trying to merge with the MEDOPS, with the medical operations and the people who really take care of the astronauts. And I think for the life sciences or for the human science, this is really important because we can do all the science that we want. In the end, you are, so to say, the customer and the end user. So we need to make sure we map onto your priorities to really make it meaningful. And here I just want to stress that I think as Europeans, we are getting very good at that, and when we look towards the other international partners, I think we are really leading in this essence that we now are building this stronger, let's say, link between MEDOPS on the one side and the research. Of course, this is more for the life sciences bit, but I just wanted to stress that because I do think that this is really important. And of course, we will also have a presentation from May-Britt tomorrow that is really going to focus on those elements. And I think for the community, it's also important to know that because then you can tailor also the research better to have a real strong application. That doesn't mean that the fundamental research is not important, but one does not necessarily exclude the other. And I think that that can be helpful as well. Thank you.
And I would also say that it's very helpful to bring the two communities together. So I guess right now we don't have like one go-to place for the priorities, but work is in progress.
Yes.
Yeah. Thanks a lot, Angelique.
Any other questions?
Well, I had a filling question, Matthias Sperl from Cologne. When you have, okay, thank you. So when you have these two ways, bottom-up and top-down science, there was a program earlier at NASA where they called this push and pull. Has that been a template for what you have in mind there?
I don't think there was any particular template. I actually think this is more common sense. I mean, we have an exploration program. It's logical that we need to do a set of activities, be it technology maturation or be it science, that support in the end those exploration objectives. So I don't know if the colleagues here want to add something, but for me it's a bit strange that we only introduce it now. We should have done it, I think, earlier. I don't know if you want to.
So for the lunar part, I know that for some of you who've worked with us on this area for the last years, I think even 10 years ago, 15 years ago, we were preparing documents that tried to orientate themselves in this direction. So I think we've been working with this in mind for a while. I did just want to reflect on, there was a question this morning for Daniel about where we think in focused science the leadership is. And I think our observation, and I think also with engagement with some of our science advisory structure, has been that where we have this research linking with the application and exploration, this is something that organizationally, I think agencies find quite hard, because often science and other areas are kind of stovepiped or separated from themselves. And this has been identified where we in Europe potentially have a real opportunity to really take a lead in terms of bringing this connection between the science and the applications of the science, and to really benefit from that. And I think there's several areas we've identified where actually we have a real opportunity to become the leaders in the world in some of these areas. And we'd also welcome your reflections on where you see opportunities here for us.
Well, I have also a question. I believe it's much more directed also to you, James, in the lunar research area, particularly also the involvement of biology, because I have seen a lot of interesting related research and foreseen ideas about humans, activities and medicine, but what is about more fundamental and basic research, biology, to be done on the moon? Because I know about a lot of ideas which were also published even recently, like a mission like BioMoon on Argonaut, but actually I cannot hear any commitment by ESA. What is in view for the future in this direction?
Okay, I'll say something, and maybe Andre, you'd like to say something too. Okay, so the things that I've shown you, specific activities we're undertaking, are things where we have an interest, we have a capability, and we have an opportunity to fly. So right now, we don't have any platforms going to the moon, other than Gateway, where there's any way you could fly anything to do with biology. So we don't have that opportunity today. I think it's something that's important to us, and we can talk a bit about where we see some opportunities there, and maybe Angelique would like to talk about that in a moment. I think BioMoon, the mission concept that several people here were involved with, I think was a fabulous study. I think it was a really a groundbreaking idea. I think it really set a path that was really unique. It was established as an idea for a way that we might use the Argonaut capability to do a really comprehensive biological study on the moon. So that's an idea that's still there. It still has some headway. We don't have an Argonaut mission assigned to us today to be able to do that. But I feel somewhat confident personally that what we've identified there is something that's going to happen. We just need to find the implementation scenario where we can make it happen. An example might be, we know that within the Artemis context, there is going to be a lunar surface habitat. ARSI are leading that. It's a European contribution because in Europe and in Italy, we are the world leaders in actually building pressurized habitats for space. And I think that the science that takes place inside that habitat is going to be primarily biology. And so I think that we need to start thinking in Europe, as we see this architecture evolving, how are we going to take our ideas and apply them to the implementation scenario that's emerging? And I don't know if, Angelique, you wanted to...
Okay, thank you. The scientists are hungry to realize this.
Hi, I'm Floris Waerts from Antwerp University. I have actually two questions. I didn't hear the role of the topical teams here so far. Is there any role which you see for that, particularly from the top-bottom or bottom-to-top? And my second, more complicated question is the following. I'm very much in favor of European identity and to do something also which is like really ESA. But to what extent do we want to invent something or work on a specific topic Whereas actually we know that at NASA side or at other sites, China or other India or other emerging countries, like working on the same topic, and to which, at what level is there like a division? Okay, you do that, we do that, so that we're not doubling the science or the efforts, but actually make it more synergistic.
Okay, first question on the topical themes. We didn't mention it, but the plan is to reopen the call. So we had it closed for quite a while. There was some discussion. What we are looking more, but this is more an internal thing, but we just try to make it more efficient because these are small contracts. They're really important, but they take a huge overhead. So we've looked internally into different ways of doing that we can keep that strong connection with the community, be it bottom up for more blue skies type of ideas and proposals, but also be it more top down, that we can have a direct, let's say, advisory type of thing, or ask for recommendations or input to work directly with the community. So we didn't mention in the slides, but it's something that we are working on and that we hope to really be able to open again soon. And I know many of you have asked about this, so I expect that there will quite be some submissions for that. With regards to this, the second question, of course, I think every agency is bound by resources and a limited number of resources. So to be fully redundant, I think, is in nobody's interest. So we should not try to replicate or duplicate. But of course, it's also maybe more philosophical question, because to some extent, you also want to make sure that you have an autonomy. So maybe some things you want to actually do on the European side, because you want to be able to have the autonomy and not be dependent on others. When it comes to the synergistic, I think across all of the domains that you've heard, physical sciences, life sciences, Moon, Mars, we have several, let's say, levels of interaction at the working level, but also higher, to make sure that we are aware of the efforts on the different agency sides, and that we can try to streamline that as much as possible. So for some things that might be, Europe is leading in this effort, let us take it. I give an example now for radiation. We are offering 2 of the 3 instruments that go onto Gateway that are focused on radiation. But for other things, we might also say, look, we're interested in, but we are not going to lead the effort because we just do not have the right elements or the competences. So it's hard to say it generally speaking, but I think this is definitely something that is ongoing and that we monitor across different levels. And just one thing I want to mention, we are of course ESA, but we represent a lot of different countries. James mentioned the Italian habitat for the Moon. We of course also need to make sure that we are aligned with what our member states are doing at the national level. And this adds another layer of complexity, but it's also of course something that can be an opportunity and a strength if we really maximize those efforts together. Yeah.
Hello, my name is Stefan Lübke. I work in Luxembourg, and it makes me proud as a European to hear what James and you have said, that this is world leading what is created here. On the other hand, my question to ESA is, in how far is ESA prepared to bring the rubber to the road when it comes to delivering the goods in time? It's about administration, it's about how to not lose many of the good ideas that are collected in requests for ideas, and how to ensure that a timely result is achieved. And my question is ESA open for public-private partnerships to accelerate?
I will answer, and if you want to add, please go ahead. I think this is a very valid question, and I actually think we do not have any other option than to make sure that we speed up and accelerate the time between making a decision and implementing, because the situation across the board is very dynamic. There's many changes happening, and if we are not, let's say, ready to act on them, we will be lost, or we will not be able to be part of the overall landscape. So I do think that's really important. We've seen some elements this morning in the presentation from the director. To give an example, the commercial mission on the ISS. I'm not saying the implementation was maybe perfect, but I mean, we did it in 10 months. So this is also an opportunity for us to learn how do we deal with this higher pace. I think for the Moon, James, you can also know that there's all these commercial opportunities that suddenly we get a shot, and then it's like, next year we're doing this. This is normally not the type of pace that we're used to working with. So we also need to adapt internally. And when it comes to private the partnerships. I know that in the directorate we are already looking into commercial in commercial partnerships, and this is something that, especially for post-ISS landscape, will become critically important. So we have many elements there that we are already pushing forward, both for LEO cargo return service, but also for the infrastructure. We're doing several studies on that, but also for the moon. I think, James, maybe if you want to comment on that, there's many elements there that we are currently exploring.
Yeah. So first, I'd like to just share what I perceive to be a frustration. So a frustration of mine, I look at what's happening internationally, things that the Chinese, the US, and others are doing, and I see ideas flying on the moon that I saw happen in Europe. And we facilitated and we supported and we built up some of those ideas. We were not able to implement them, and now they're flying. Other people are realizing them, or other countries are realizing them, or Europeans are realizing them in partnership with agencies that are not us. I personally, it's a frustration for me. I think that as I look forward, I see an ambition to expand and to grow, to uplift science, as Daniel has indicated. I take tremendous solace in that. I see great opportunity in that. I think that, so in terms of the preparatory work and commitment, I see it there, at least at that level. I think that in terms of being fast, we're getting better at that. So NILS, we went from, okay, let's do that, to flying it in 2 years. Right? I mean, that's extremely fast. Now, that's only possible because you're building on something that's already very mature as a technology. So, but there are opportunities to do that. In terms of commercial partnerships and finding new ways of doing things, we are exploring new things. So in Angelique's presentation earlier, you heard about this Pulley thing. So Pulley are a small company in Hungary. They had an idea, working with CERN, built in it a sensor, completely without working with any agency, made a deal with Intuitive Machines to fly this thing to the moon, just to see what would happen. And they're doing something completely new, and we're becoming involved. And it's a bit of a test case. Like, what does that mean to get involved in a commercial partnership where the commercial partner has done all the work and we're just coming along later and taking opportunity and trying to create benefit from it, and stimulate a new way of doing things. So it's a test case, and we'll see if it works, but we are proactively exploring some of these new ways of doing things. And so I think that in the future we'll see a combination of perhaps longer development times for some ambitious, perhaps very novel ideas, with some rapid developments alongside that, and some perhaps a bit slightly more novel ways of doing things too. And I think that would be a kind of a healthy and dynamic program. I hope we can see that. And I hope that the ideas that people here are generating, we're able to implement. I would love to see that happen more. Yeah.
Maybe one last question before we go to the next presentation. If there's no question, I just want to make maybe one additional statement. So, I mean, I know we have a full program in the next 2.5 days, but really this is also an opportunity for you to speak to us. So if you have any suggestions, ideas, things that you think we are overlooking or that we're not considering, or anything really that you have in terms of feedback, this is really the type of event where we also welcome any type of feedback that you have, whether it's positive or negative. I think it's important for us to know what are your concerns, what are the things you're thinking about, what are things that you're missing or that you actually like seeing. As long as the feedback is constructive, I think we would welcome it very much. So please feel free to speak to me or anybody from the team here, so that we can also take it into account. We are currently in a critical stage of preparing, let's say, for the next ministerial conference, where we will then outline the plans for the years 26, 27, 28. But of course, your feedback on that is also really important, and anything that you have for us, we would really appreciate it. And all of the sessions, we are, let's say, taking parts of the discussion, and we will also generate a report on that. But again, anything that you don't feel comfortable sharing for the full forum, or that is a bit more, let's say, a detailed discussion, please feel free to approach us. I think this is really important. So thank you very much for your attention. We will still be here. So again, if you have any follow-up questions, you know where to find us. And I think we should move to the next presentation, but we are waiting on Sławomir. Okay. Yeah, if they are ready for it. Okay, so we're just going to quickly check whether we do the break and then we do the presentation later, but I don't know if that will work. So just give us 1 second. We will do the presentation now, and then we do the coffee break later. So, Sławomir, the floor is yours.
Thank you so much. Okay, thank you. I'm sorry if I'm late, or maybe 3, 2, 1, and then go. This is for the slides, no? So I wanted to present to you today an update on Axiom-4 mission. So I don't know if all the international community knows about Axiom-4, so I wanted to give you some basic information and the advancement of the training that we are doing, and I'm going through with my crew for the preparation of the launch sometime next year. Here on the slide, you can see our team. So our team is truly diverse. We come from 4 different countries, from 3 different continents. The commander of our mission will be Peggy Whitson, a very established female astronaut from NASA, actually the most experienced astronaut in the history of NASA. So she spent 675 days in space, and I'm very honored to be led by her as a commander. Another colleague who will be the pilot on the mission comes from India, Shubhanshu Shukla, Shuks, and he was selected and recruited by the Indian Space Research Organization in 2019. There were a selection of 4 astronauts, and 2 astronauts were assigned to the mission, one as backup, one as prime, and Shuks will be the prime and the pilot of our capsule. Myself, as the ESA astronaut from Poland, project astronaut, and I will be following as a second project astronaut from ESA after Marcus Wandt from Sweden, who was assigned to Axiom-3 mission and flew to the International Space Station in January this year. And the 4th person, the second mission specialist, Tibor Kapu from Hungary. Hungary presented and pulled and defined their program a bit outside of ESA separately as a national program, and they signed an agreement directly with the company Axiom Space. So what's quite interesting, within our crew we have 3 crew members and the commander Peggy from Axiom Space, and with 3 different objectives and 3 different contractual scenarios of how to execute space missions in a new commercial formula. How we are going to sit in the Dragon spacecraft, this is exactly that. The seats are numbered from 1 to 4. I will be sitting on the seat number 1 as a mission specialist 1. Seat number 2 is a commander seat. So I'll be on the left-hand side of Peggy Whitson. On her right-hand side will be Shuks as a pilot. So commander and the pilot, they will sit in front of console and commanding our spacecraft. And me and Tibor, who will occupy seat number 4, we will be helping out with having different job description. On my side of the capsule is mostly an environmental control and life support systems. On Tibor's side is more emergency scenarios and, for example, the life raft if we happened to need it in the oceans if the capsule, for example, is flooded after our splashdown. Going further, probably most of you know how the Dragon spacecraft looks like. Here on the slide, on the left-hand side, you can see it spans almost up to 9 meters. It is around between 3 and 4 meters of the diameter. There is a pressurized section, or let's say from the top down, there is the nose cone. Inside of the nose cone opens, approaching the ISS, and exposes the docking port, and this is how we are going to dock to the ISS. On top of the nose cone, there is also thrusters that allow to the Dragon spacecraft for trajectory control. Below, we will be sitting in the pressurized section for crew. So there will be 4 people. We will take our pressurized, inside of the pressurized section, also some cargo. And then below the Dragon spacecraft, there is a trunk. It's not a pressurized module. Here on the slide, you can see how a person looks like compared to the Dragon spacecraft. On the trunk, on the other side, on one side, you have radiators. On the other side, you have solar panels. So this is how the spacecraft generates power, as well as dissipates heat towards the vacuum of space. And the spacecraft will be sitting on the Falcon 9 rocket that is composed of 3 main sections. At the top, there is the Dragon. In the middle, we have a second stage that is a cryogenic stage that will propel us in the further part outside already of the atmosphere. And at the bottom, there is a big booster that is used at the launch pad to propel the second stage and the capsule outside of the atmosphere. What we intend to do on the Polish mission is there are 3 main objectives. And this is similar to multiple missions, but on the other hand, these are the mission objectives from the Polish side, mostly focused on technology and science, mostly on technology. And that's why a strong link with Ministry of Technology in Poland and science with the Ministry of Science. I don't know if my videos will work. I'll try. And here you can see a small snippet how it looks, how the work on the International Space Station looks like. So you can see multiple European astronauts here. This is Andy. This is Marcus, so from my selection, who was flying through the ISS, and I hope to be able to do it sometime next year. And the ISS is a big science laboratory that we would like to use to execute our science and test our technology demonstrators. The second part is education. We would like to have certain educational events, maybe as live in-flight calls, maybe as certain recordings for kids at schools, for students, and be able to directly inspire the future generation of scientists and engineers who are going to build the space sector. And obviously inspiration, this is the third part of the mission, and I hope, I don't need to convince you, but space inspires me. I hope inspires all of you because you are sitting here today, but I think and I hope that the Polish mission will inspire millions in Poland to follow our steps. Here you can see the small video. The second video is myself flying on the parabolic flights, and I was playing in microgravity with water. I don't know if you will be able to see, but I create a water droplet, and I try to send this water droplet to the window of the microgravity glove box. So this is one of the glove boxes, let's say a container on the ISS. In microgravity, as you can see, it migrates towards the window and it sticks to the window. So you will be able to see how it sticks in a moment. And even on such small experiment, we can run a beautiful educational program for kids at school to tell about microgravity, about the surface tension of water, or hydrophilic, hydrophobic windows and certain surfaces. And I think this is an extremely good platform to educate. Let me go to the research component of the mission. So we have big Polish contributions. There was a call of ESA in August 2023 for the first time to select Polish experiments. Here on the slide you can see multiple of these ones. There are certain names, but what we intend to do from the Polish side is to study mental health of astronauts and how it is to work in such stressful conditions. Certain neurofeedback. Also, this is This is more on the psychology studies of medical research. Human gut microbiota, this is an experiment that will study the microbiome of astronauts on short-term missions and how it changes in a spaceflight for better diagnosis and to better understand physiology mechanisms in our body. The next one, Leopard ISS, this is a technology demonstrator. This is an engineering component and will place a high compute platform on the ISS to be able to have, let's say, this platform that will serve to test algorithms, software algorithms directly on the ISS in space on the platform. I think it's a beautiful potential future possibility to use platform as a service. Maybe let me describe just a couple of them. PhotonGraph is an experiment that studies human brain activity in near-infrared spectroscopy that allows, as per research of this research team, this allows to correlate stress factors and environmental factors as well as focus with a direct measurement, objective measurements from the brain. There is Spell's volcanic algae to study biological organisms and algae here that generate oxygen and their survivability in microgravity as well as radiation environments on the ISS for future potential bioreactors. Wireless acoustics, I think Daniel in the morning mentioned on this experiment, tends to study the environmental noise using acoustic dosimeters for hearing impairment of astronauts as well as diagnosis of systems. On education, I already expanded, so maybe I'm not going to talk too much about that, but this is not only about polar science. We can and we will belong to the European scientific community and hopefully execute certain established ESA science and contribute to a broader scientific community. Studying bone health and bone on ISS, these are two experiments studying the health of bones and demineralization of bones in microgravity. We have some fluid physics experiment and certain facilities that we might use that are placed in Columbus, that is our European laboratory. And not only that, together with ESA and Polish science, there is a potential possibility for much broader collaboration. As I said, we are flying with like 3-4 different countries, and we have this opportunity to establish science relationships between Poland, India, Hungary, and the United States that hopefully will last not only for mission Axiom-4, but will last many more years to come. And a bit towards the training, how it looks like. So as you can see, I'm sitting in the masks and with different headphones and in different places. Most of these pictures are from NASA and Europe in Cologne, where we have the astronaut center, as well as JAXA in Japan, where I happened to be last week. The first picture is how it looks emergency mask on the ISS, and we need to test emergency cases and behave in certain scenarios of fire, rapid depress when we lose the atmosphere or there is an ammonia leak, to be able to behave in a proper way and save ourselves, the crew, and then further on, if possible, the vehicle. The second picture is my picture where I had a chance to sit with Capcom. Capcom is a console position in Houston that talks directly to astronauts and guides them through their day on the ISS. I had a chance when I was sitting on Capcom to see Don Pettit, who is a selection of NASA of '98, a very well-known astronaut, an engineer by trade, and we were guiding his day through one of the European experiments in Columbus on the biolab. The third picture is myself being exposed to high altitude chamber conditions at 30,000 feet, so roughly 10,000 meters, to see with the lack of oxygen how it impacts our perception, how it feels to be deprived of oxygen in hypoxic state, in case if it happens on the ISS or in the capsule, to be able to recognize our symptoms. Obviously, on the fourth picture, there is a lot of medical operations, medical emergencies, and how to cope with that if one of our crew members or ourselves happen to be in one of the emergency like that. And there is many more trainings audiovisual, photography, videography, how to operate different hatches, experiments, science racks, as well as systems in terms of power, cooling, orbital trajectory, avionics. I'm not going to go too much on this slide. Daniel presented this slide in the morning, but I wanted to iterate a bit on what is the strategy towards in near future and maybe mid-future of ESA. Here on the slides, you can see already established and committed projects that are both in low Earth orbit towards the Moon and towards Mars. And the very extensive presentation of Daniel this morning showed you most of these directions. Where is the next step? We have a cargo mission and cargo return service to the ISS that is being in early phases of project assessment now, and what will be the post-ISS era? This is a good question on low Earth orbit. Obviously, Argonaut project was discussed quite a lot today, but there is a lot of potential possibility for small missions and small science and small spacecrafts, as well as lunar surface exploration, and also certain new projects towards Mars. If we go post the next ministerial, we can see multitude of projects appearing and multitude of science as well as technology demonstrations that will have to happen to maintain and continue our direction in Europe for our autonomy, independence in terms of technology, but also a big global collaboration so Europe can be a global partner in that phase. And this will happen also on low Earth orbit towards Moon and Mars, finally, that is up and coming direction. What's next? This is my last slide for you. Obviously, I am looking forward to next modules of training and our science and technology development towards the mission. This is a big objective, and I hope we will be able to seize this opportunity and to use the mission to perform beautiful science, technology demonstrators, educational program. Next will be the mission. So everyone wonders what will be the date. I do not know, I cannot really tell you the exact date, but this will be spring, summer of 2025. So in a couple of months, the mission is targeted to launch, not earlier than spring 2025. We already see the increase of contribution of Polish science at ESA, and there is more pronounced Polish presence in different calls. And hopefully with the mission will attract much more attention, and new generations of students and engineers would like to contribute and continue their career in science and technology. Obviously, there are new discussions starting towards the ministerial of 2025 at ESA, and hopefully here we are looking to more increased hunger and ambition from our side, and what will be our midterm goals in terms of contribution on the European scale of building the technology. But already today we are building a certain post-Axiom-4 plans in terms of science and new projects, and I can't wait to see them being realized in the next years, at this decade, in the 20s and 30s in the next decade. And I know that our ambitions will grow. So thank you so much. And I'm happy to take your questions. I'm sure there will be some.
Hi, so I'm Rebecca. I work at MEDES in Toulouse, in a ground-based facility. First of all, you have a big hello from all of MEDES. Everybody was super excited to see that you went this far. My question is regarding Axiom missions in general, and how can we go about presenting ideas for science? Life sciences especially, that could be done on Axiom.
Thank you, and hello to all MEDES from my side. It was a great stage of the recruitment, and all of us, remember that. It was just great, and thank you for doing all the medical screening for us. How to how to do that, I can tell you a bit more on the Polish side how it happened. And we decided to go this direction and invest in the space flight with Axiom. It's a short-term mission, so it's not, it spans over 2 weeks of science. On Axiom missions, more or less, there is around 80 hours of science that can be executed. 80 hours is a lot in 2 weeks. So a full increment, just for comparison, a full increment that is 6-month mission normally is 143 hours, if I'm not mistaken. So in 2 weeks, it's really amazing how much science technology demonstrators can be done. In Poland, we had the call at ESA in August 2023. We had 66 proposals that were gathered over 4 weeks that the call was opened. I think everyone was quite surprised of how big potential in the Hungary is there. And out of that, there is multiple that were selected for development, and you could see all these ones on the slides. I am myself an engineer, so I look obviously forward to contributing to my field of science, but I'm fascinated by life sciences. Our complement, I think, has more life science experiments than technology experiments. That was a very big surprise for me. I think it's great. I think I can learn a lot, and in the fields that are not my core domain, but as astronauts, we learn basic science in each field, and we hope to be performant in whatever comes next as the experiment, so I can't wait. And yeah, I think it's just amazing that in 2 weeks you can execute 80 hours of science. I don't know if this will be exactly the same for each Axiom mission, because each mission might have different objectives, but for us, Hungary, Poland, and India, we have our main objective is technology demonstrations, science, and obviously followed by education. So I think this will be a big chunk that what we will do. Thanks. Thanks for the question. No more questions. Okay, excellent. Thank you so much for listening. And yeah, I give the microphone to Angelique.
Just to say that we have a coffee break now for half an hour, and we start again at 4 o'clock. See you soon.